Resting in the hangar, this Cessna 402, registered as PKWLW, presents a seamless exterior. Up close, however, the structure reveals itself as an intricate assembly, bound together by thousands of individual metal fasteners. In the air, an aircraft is subjected to extreme environmental forces. Severe vibration and shifting cabin pressure constantly flex the metal, causing dangerous microscopic fatigue over time. Because of these relentless forces, a single hairline crack or one missing rivet serves as a potential starting point for structural failure. Flight readiness depends on the microscopic integrity of the entire physical shell, a baseline that must be verified before the airframe is ever cleared for takeoff. This verification follows a 17-step protocol designed to map the aircraft's structural health, identifying minute flaws before advanced scanning technology even touches the skin. The absolute first rule of this process is safety. Inspectors are strictly required to use personal protective equipment, outfitting themselves with hard helmets, heavy safety shoes, and protective earplugs. They need that gear because the hangar environment is unforgiving. Mechanics must navigate tight spaces under the wings and manage constant collision risks. Despite our automated aviation technology, the ultimate primary sensors keeping passengers alive remain the trained human eye and the human hand. Before an inspector can find abnormalities, they must establish the baseline of a healthy aircraft. We start by mapping out its three main macro zones. First is the fuselage. This is the semi-monocoque main body, a design where the exterior skin shares the physical load, built to protect the payload and crew. Next are the wings. They function as a cantilever structure, relying on an internal skeleton of long spars and crossing ribs to support the entire lifting force of the plane. Finally, the empennage. Located up a rear, this tail section consists of horizontal and vertical stabilizers that dictate the aircraft's directional balance in the sky. These three major zones must distribute flight loads continuously across their surfaces. A structural weakness in one zone inherently compromises the integrity of the whole system. Transitioning from the large skeletal structures down to the skin, we find the material holding it all in: aluminum alloy. It is the material of choice because it is shiny, lightweight, and highly durable. To cover the plane, engineers used the lap joint method. As this cross-section shows, these alloy panels are meticulously overlapped to create continuous, smooth aerodynamic surfaces. To hold those overlaps in place, the aircraft relies on a massive fastener system. Thousands of rivets permanently lock these lap joints together, preventing the panels from shearing apart in the wind. This interconnected network of tiny mechanical fasteners acts as the true load-bearing web, absorbing the immense tension of flight. During an active inspection, mechanics hunt for deviations in that metal skin. They point flashlights at oblique angles across the panels and use magnifying glasses to search for tiny shadows that shouldn't be there. On PKWLW, the search uncovers physical force damage. As highlighted on this wingtip, inspectors found hidden dents right by the right wing fuel tank, along with surface scratches on the tail. This inspection table reveals joint fatigue. The wing and empennage joints are flagged as abnormal, with notes specifically indicating several missing and loose rivets. This dangerously unevens the structural load across the remaining pins. Then they spot signs of material degradation. The dark brown, rough textures of corrosion are discovered eating away at the landing gear skin and the moisture drain holes. These specific anomalies, the dents, the missing rivets, and the creeping corrosion, are the physical scars of the silent, ongoing war between the aircraft and the elements. Finding a list of defects does not mean the Cessna 402 is unfit for flight. In fact, identifying these issues confirms that the diagnostic system is functioning as intended. Airplanes are built with structural redundancy. They are heavily over-engineered so that a single missing rivet or a patch of surface corrosion will not cause the plane to fail. But while the plane has built-in redundancy, the tolerance for ignoring cumulative minor damages is zero. Complacency is the true enemy. Flight safety is a reality maintained by the effort of technicians carefully wielding flashlights and mirrors in the hangar. Gravity is defeated daily through the relentless, microscopic discipline of the human inspection process, ensuring the airframe remains as reliable as the engines it carries.